Hi everyone, back for another video. We're going to cover action potentials and propagated series of action potentials, which is called a nerve impulse. And so, just to back up a little bit, if I draw the region of a neuron, so the axon initial segment, we won't draw the soma and dendrites over here. Right, we've got our axon initial segment and then the axon itself, and we don't need the other end of the cell just yet. We won't focus on that. Right, so if I highlight this region, the very beginning of the axon as the axon initial segment, label that. Right, axon initial segment. So again, that's the first place on the neuron after the soma and dendrites where we have voltage-gated channels. So remember, the only way to get an action potential, and let's add a voltmeter here, where we're measuring the inside relative to the outside of the cell right there at the beginning of the axon. And we can track our voltage right there as graded potentials occur on the soma and dendrites, and then through electrotonic current would change the voltage at the axon initial segment. So it's important to realize, again, that only EPSP graded potentials could potentially cause an action potential. Now, they don't always, because again, they can come in various sizes, some of them not being large enough to reach threshold of our voltage-gated sodium channels here. So we have to assume, though, if we're going to talk about action potentials, that an EPSP or series of EPSPs occur that get us to threshold at the axon initial segment. So if we have the graph of our voltmeter at this point, at that location, and we can move this voltmeter down and measure a different action potential that's generated later after one is generated here. So we sort of just have to pick a spot where we're measuring the voltage and then record our action potential. And so if our cell is at -70, right? Remember that's our VM, our voltage of the membrane. Resting membrane potential somewhere around -70. And we get some EPSP input, right? We could, let's put our threshold on here, at something higher. It's probably 5 to 10 millivolts higher, so -65, -60 millivolts. That's the threshold, again, of the voltage-gated sodium channels. So if we have an EPSP arrive, and it's a small one, it would arrive and then dissipate, and nothing would happen, right? We would not get an action potential. However, if that EPSP is large enough and gets us to threshold, right, then all of a sudden we get an action potential and we get significant depolarization due to sodium influx. Okay, so let's show our sodium influx occurring, right? And so that makes the cell more positive on the inside, which is what's happening here. Actually ends up somewhere in the ballpark of +30 millivolts, which is not all that important, but it does take us toward the sodium equilibrium potential. It doesn't quite get there. Sodium equilibrium potential is about +60, +65 millivolts. And the only reason it doesn't really get there is, number one, other ions have the potential to move. Nernst potentials are theoretical. And the channel closes before that would occur. Now, what has to happen, again, at that same spot, different color here, immediately after we depolarize is we need to repolarize. And so reaching threshold is the threshold of the sodium channel, but it's also threshold of the voltage-gated potassium channel. The potassium channel is just a little bit slower. And again, this is time down here, and it's in milliseconds, right? And this whole thing would be multiple milliseconds, not very many, because an action potential only lasts about 1 millisecond, 1/1000th of a second, so they're very fast. So We depolarize, but we need to quickly repolarize, and that happens through potassium efflux. So very quickly afterward, at the same spot, our green pluses here would be potassium, our yellow ones would be sodium. And the sodiums would come in first, and the potassiums would come out second. So here comes our repolarization due to potassium efflux leaving the cell. Now, if we don't have another EPSP at the moment, we would actually hyperpolarize a little bit, right? Go past normal resting membrane potential, and then we would come back up. I'll find my resting potential here. Come back up to resting potential right about there. Right, so we have a little hyperpolarization after the action potential. Now, one of the things, that we have to talk about with regard to this is that there's a refractory period. Well, there's actually two refractory periods. There's an absolute refractory period and there's a relative refractory period. The absolute refractory period is the period during an action potential during which you cannot get another action potential. It's kind of like you can't get an action potential on top of an action potential. So it can't just depolarize and then stay depolarized. And that's because we are refractory basically through that whole spike. So that the length of that bar, which is about 1 millisecond, would be the absolute refractory period. The relative refractory period, which I didn't say much about in class, would extend throughout most of the period of hyperpolarization, or even this little span right here where we're not hyperpolarized, but potassium is still leaving the cell. The only thing about the relative refractory period, RRP, that we need to know is that it's harder to get an action potential because you're farther away from the threshold, right? So we need a bigger EPSP to get to the threshold when we're in the relative refractory period. That's not a big deal. The absolute refractory period is a huge deal because it means that we can't get action potentials one on top of another, and that's important because information is coded in the frequency of the action potentials. So if it's one giant action potential, there's no such thing as a frequency, right? It's frequency of individual events. So we have to get individual spikes. It can't be one long depolarization. That wouldn't really mean anything. So the absolute refractory period helps us with that. It means that we cannot reach threshold and get another action potential until right about here, right? If our stimulus was still there, our EPSP was still large, you wouldn't see this, and we would spike again, and we could just sort of continue that pattern. Again, measuring this at one spot, right? The other good reason we have for an absolute refractory period is that once our action potential travels, and again, now it's called a nerve impulse, a wave of repeating action potentials. Once our action potential is over here, if the membrane, remember the local current, let's draw some ions moving here, right? If the action potential is right here, that electrotonic current can go backwards and forwards. Now forwards, it's going to continue to generate a new action potential. Backwards, it's refractory. In other words, the action potential was just here, right? It's traveling in this general direction, right? And so the electrotonic current is bidirectional. It can go or any direction, right? And so it can actually go backwards. And if it wasn't refractory here, we could get another action potential, which would travel backwards, right? And remember, once that one gets to here, it could generate an action potential that goes forwards. And so you just have action potentials running back and forth pretty much indefinitely. So in the absolute refractory period, it helps us avoid that. It allows us to have discrete action potentials so we can have frequency-coded information, and avoids this sort of back and forth, what are called retrograde action potentials, running in the wrong direction backwards. Okay, so we've got our action potential at one spot. Now remember, let me erase it a little bit here. Back to having our action potential just here for the moment. We get electrotonic current. Some of that will go forward down the action potential or down the axon, and stimulate the opening of the next set of voltage-gated channels, which will lead to electrotonic current, which depolarizes the next segment of the membrane where we have new sodium channels and potassium channels, which generates electrotonic current. right? And that's called continuous propagation. In other words, every segment of the axon is stimulated. You get opening of voltage-gated sodium channels, followed by opening of voltage-gated potassium channels, and you get an action potential at every single area, right? And remember, we'd have to take our voltmeter and keep moving it downstream to measure the action potentials at those locations, right? That's continuous propagation. The speed of continuous propagation is based largely upon the size of the axon, the diameter of it. That is true because the diameter is linked to the Ri, the resistance of the cytoplasm, or the internal, the I for internal, resistance. In other words, that's the resistance along the cytoplasm. And the bigger the axon diameter is, the less resistance there is. And so our electrotonic current more effectively, remember, some of our electrotonic current does leak out, right? But the lower the resistance along the axon itself, the less will actually leak out, right? Because this is the path of least resistance for our current flow. And it will, our length constant would be larger and propagation velocity would be faster. So larger axons are faster axons. Now, we could also add, and I have to draw something else here for a second. We could also add myelin. Right, where we have the axon wrapped with layers of membrane of the myelinating cells, either oligodendrocytes in the CNS or Schwann cells in the PNS. And what they do is they create insulation, electrical insulation around the membrane of the axon. And remember I had this sort of leak coming out, right, that would pass through the membrane before. Well, now we have, right, I'm putting X's over those. Right now we have increased resistance across the membrane here because of all these layers of myelin. And so now we would get less current leak out of the cell because Rm is high, which makes our length constant large, which means we more effectively depolarize. Our electrotonic current travels farther and faster. We get to the next node, generating an action potential, better electrotonic current to the next node, new action potential, better electrotonic current. And so that makes myelinated axons faster conducting than non-myelinated. So add those two things together, a high Rm and due to myelin, and a low Ri due to a large axon means that the fastest axons are both large and myelinated. Okay, I think that's about it for action potentials. We've got our refractory periods in. Keep in mind, we're going to get to the end of this axon and we're going to run into the synapse. And so we have to then release the neurotransmitter and start talking about whether or not our synapse is a chemical synapse or an electrical synapse. Okay.